Okay, so there was one request to do this problem from the review. Use the convolution theorem to find this inverse Laplace transform of 8 over s squared times s squared plus 4. So I copied it down here. And the approach to this problem is we're told to use the convolution theorem. And convolution is this property right here that L of f star g is f times g, where f star g is that weird integral called convolution. And I'm just copying it down to my tablet. Okay, got a little bit crammed right there at the end, but the convolution integral is f star g is the integral from 0 to t of f of tau g of t minus tau d tau, and the convolution theorem tells us that the Laplace transform of a convolution is the product of the functions in that convolution. The inverse of this is that L inverse of a product of two functions is going to be the convolution of the inverse of those two functions, where convolution is indicated by the star and is not the same as multiplication. So if we weren't told to use convolution for this problem, we would recognize it because we have a product of two things inside a Laplace transform. So we're in the space of S, so we're in the space of the capital letters that we use when we're denoting regular functions with lowercase letters, and then Laplace transforms of those functions with uppercase letters. And the property that's related to multiplying two things together in the space of Laplace transforms is this convolution theorem. So the two products I'm seeing here are s squared and s squared plus 4. If those two things weren't together in the denominator, then these would be functions that I know how to take the inverse of already. 4 is 2 squared, so if I had 2 over s squared plus 4, I know that that is a sine function. And then what's left over is 4 over s squared, which I actually might want to pull a 2 out. Let's check that. S squared belongs to 1 factorial. So actually, I think I want to take the whole 4 out front, like this. The reason I group them that way is so that they look like two things that I can easily take the inverse Laplace transform of. 2 over s squared plus 4 I would get from k over s squared plus k squared, so this is going to be sine 2t, 4 being k squared. And then L of t to n, I'm going to use this property, n factorial over s to the n plus 1 for n equals 1 to get just t. And I'm going to not write the to power 1 there because we usually don't write it like that. So if I'm taking L inverse of the product of those two things, I actually want to have the convolution of my functions t and sine t. So my inverse is actually going to be 4 times t convolution sine 2t. And then all I have to do is pick what my f and g are in order to plug in and evaluate my integral. So what do I think is going to be easier? I think I'm just going to keep it in the order it's in, that f is t and g is sine 2t. I don't really like putting a t minus tau inside the g. but if I don't, no, it's okay. I'm going to do it the other way. Sorry. I'm likely to make a mistake if I try to have like a u sub inside the sine. So it's better to do f is sine 2t and g is t. So then that means that f of tau is sine 2 tau, and g of t minus tau is t minus tau. So then 4t star sine 2t is going to be 4 times the integral from 0 to t of sine 2 tau times t minus tau, all of that integrated with respect to tau. And I can distribute sine across the t minus tau to turn this into two integrals. So this is going to be 4 integral t sine 2 tau d tau minus 4 integral tau sine 2 tau d tau. And those integrals go from 0 to t. Because my integral is with respect to t, with respect to tau, this t in the first integral is actually a constant as far as tau is concerned. So when I'm thinking about evaluating these, I can go ahead and pull that t out front. I'm looking at integral from 0 to t of sine 2 tau d tau. But for the second integral, the tau is the variable I'm integrating with, so I do have to leave it inside. So that one's just going to remain 4 integral 0 to t tau sine 2 tau d tau. And I'd like to copy this all over to the next page to start evaluating my integrals. Okay, there it is. And my first integral is easy. It's just the integral of sine. And I'm going to pull out a 1/2 because of the 2 inside, and then I just look at my equation sheet that tells me integral somewhere. So when I integrate sine, it's going to throw a negative sign, I think. Let's think about that. Derivative of cosine is minus sine. So integrating sine is minus cosine. Okay. So it's going to be minus sine 2 tau evaluated, minus cosine 2 tau, evaluated from tau equals 0 to tau equal t. And then the second integral is a little bit harder. I'm going to have to do integration by parts, unfortunately. So I'm going to do minus 4, give myself a big bracket to work on that. My integration by parts is the integral of u dv is uv minus the integral of v du. And because this is a definite integral, I do have to hold on to my bounds. Just everywhere I put in functions, I'm still going to do evaluation from 0 to t. And in this case, what I would like to do is take my u equal to tau, because that means my du is d tau. So the t times sine is the thing that's causing me trouble to integrate. I'd like to integrate without the t. So using it as the thing that becomes a derivative is what I want. That means my dv is sine 2 tau d tau, which means my v is that same integral we just took, minus 1/2 cosine 2 tau d, and the d tau goes away. So then plugging in the formula, I'm going to have u times v So tau times minus 1/2 cosine 2 tau, evaluated from 0 to t, then minus the integral of v du from 0 to t. And because my v has a minus in it right here, I'm actually going to turn that minus into a plus. 1/2 cosine 2 tau d tau. So I've got 2t minus cosine 2 tau evaluated from 0 to t minus 2 You know what, I'm going to leave that minus 4 out front. No, it's okay. I'll move it in. So that minus 4 times minus 1/2 is actually going to become positive 2. Then tau cosine 2 tau evaluated from 0 to t. And then minus 4 into the next integral becomes minus 2, integral from 0 to t cosine 2 tau d tau. And integral of cosine is just going to pull out another 1/2, and then I know it must be the one that becomes positive because sine became negative, and I evaluate that from 0 to t. So now all I have to do is plug in t, plug in 0, and I should get the answer. So I've got 2t times negative cosine 2t plus cosine 0 plus 2 times t cosine 2t minus 0 times cosine 0 is just 0. And then minus the 2.5 cancel out, and I'm just going to have sine 2t minus sine 0. From my formula sheet, I'm not told if sine 0 or cosine 0 is 1, so I have to use my brain for a second. I think cosine 0 is 1 and sine 0 is 0. I'm going to go with that. On an exam, I wouldn't hold you to memorizing that. So I've got minus cosine 2t plus 1 plus 2 cosine 2t cosine 2t minus sine 2t plus sine 0, but sine 0 is 0. So this becomes minus 2t cosine 2t plus 2t plus 2t cosine 2t minus sine 2t, or 2t minus sine 2t. And when I look at this, I have something that's only in terms of t, not s, and not tau. So I did take the integral in the way I meant to, which was to get rid of all the taus, and then I did take an inverse Laplace transform because I ended up with something that depends on t.